yeah, like I said, we're going to do these two today. We'll do 41 and 42. I guess we'll get started with 41, digitDegree. Everyone ready? All right. So what is a digitDegree? Well, it's something we're defining this problem as basically being the number of times. Oh, okay. Imagine you've got a number and you add up all the digits, add them together. That gives you a new number. How many times are you going to have to do that until your number eventually reaches something that's just one digit long? So basically, if you start with something that's one digit long, like 5, it's going to take 0 times because it's already one digit. If you have 100, it's just going to take 1 time because 1 plus 0 is going to be a one-digit number. That's just 1. And then if we've got something like 91, so we add 9 and 1, we get 10. That's still 2 digits. We add 1 and 0, we get 1. That's 1 digit. It's what we're looking for. It's good. Okay, so basically, once we get to 1 digit, we're stopping there because, I mean, there's nothing to add up. You just add up the 1 digit. You're just going to have the same number over and over again. So basically, it would be like an infinite loop if we were to keep repeating. Okay, so basically, that's what a digitDegree is. That's how we're defining it in this problem. And we want to go ahead and figure out what the digitDegree is going to be for a given number, n. And something to notice, normally I wait until a little later to draw our attention to this, but look at the constraints on this. That is like something. So n goes from 5 all the way to 1 billion. Okay, so we should be ready for that. We should be prepared for some basically very, very large inputs here. It's a possibility. Okay, so I know that in this problem, at some point anyway, we are going to want to add up all the digits of a number. We're going to want to get the sum of all the digits of a number. So that's probably a good thing to start with. We'll write a function. It's going to be called digit sum. And it's going to take an input of num for number. Okay, and so what are we going to do with this? Well, we're going to say, let's keep track of this variable called sum. And that's going to be the thing that ultimately will be returning at the end of this. Now, what are we going to do? We'll do a loop. We could do a for loop, but I'm going to do a while loop for this one because there's not really, we're not really going to have an initial condition or, I guess we could do this in the form of a for loop, but anyway, a while it's fine for our purposes. So what do I actually want to be doing here? Well, basically I want to add to sum the final digit. So sum plus equals the final digit of num. Well, what is the final digit of num? It's what we would get if we divided it by 10 and then just took the remainder of that, okay? So the remainder when we divide by 10, that's going to be the final digit. So like, for example, let's say we're looking at this 91 here, divide 91 by 10. Well, 90 divided by 10 is going to be 9. So 91 divided by 10, the quotient would be 9, but the remainder would be 1. There's that 1 left over. Okay, so basically, that's num mod 10. So that's what we're doing. But then what we want at the end of that is basically we just want to iterate this over so that the next time it does the num mod 10, it'll get the 9 instead of the 1. So we're going to say num is assigned the value of math.floor num divided by 10. There we go. Okay, and let's see if this is working. So we'll say return, what was it called? Digit sum? Digit sum. Oh, God. Okay, that's kind of annoying. I probably should have called it something different, like get sum or something like that, just so that the autocomplete wouldn't think I'm talking about digitDegree. Anyway, so digit sum of what number do we want to use? Let's go with 125. So it should be 7 in this case, I guess. Or no, 8. Okay, great, 8. Good stuff. All right, so great. It looks like that's working. I mean, we could make it longer or something. 7,925. So what's that going to be? 14 plus 9, 23? Yeah, 23. Okay, cool. So I'm convinced that digit sum is working. I think we can probably move on from here. Okay, so really, what are we trying to do in this problem? Well, we're trying to find the degree, right? So kind of similar to what we have in this smaller function, I'm going to start with degree, and it's going to start at 0, and I'm going to return it at the end. Cool. All right, so then what are we going to do in between? Well, basically, we're going to say for, and I don't know if I'm going to have an initial condition here, but I do want to say, n is greater than 9. Or I could also say greater than or equal to 10. But the main thing is I'm trying to say keep this going while n is still something that's not a single digit. So basically if it's greater than 9, it's got to be at least 2 digits. Okay, and then I'll just say degree plus plus at the end of that. So every time it completes a loop, it'll iterate the degree. So notice if n was not greater than 9 to begin with, it won't even enter this loop. So we won't need to worry about that. Okay, so basically from here, let's see what we're going to do. We'll say n is assigned the value of digit sum. Yeah, I really should have called that something else. Digit sum of n. It's going to be its own digit sum, and we'll keep that going until this is the case, or until this is not the case, until it's 9 or less. At which point it'll say, okay, great, we're done, and the degree will be the number of times we had to do that. So it seems like it's answering the question. That's good to see. Let's see if it's going to pass the hidden test as well. Let's just go right for it. Oh, yeah. Okay. So that's good. Nice job. Let's close this for now. And you might be looking at this and wondering, well, why not just take this thing? Like, this seems like an initial condition, right? Why not just take this and put it right in your for loop right there? Like, wouldn't that be a good fit for it? I mean, it seems like that's what this spot is designed for, right? Setting up your initial condition. And yeah, I mean, if we were talking about like pre-ES6 kind of stuff, then I would agree with you. But the thing is, because of this let here, it's going to cause a problem because it's going to say, well, degree is not defined. And if you're not familiar with let or const and that kind of stuff, this might seem really confusing because it's like, it's not defined. What are you talking about? It's defined right here. Like, we're literally defining it right here and then trying to call it like 2 lines below. How's that not defined? Well, it's because of the way let works. So just like, for example, this variable sum here, right? Like if I was outside of this function and I said return sum, it's not going to know what I'm talking about. And in fact, even the editor knows it's not going to know what I'm talking about because, like, notice how this one's in green, all the others are in blue because it's saying like, oh, yeah, you're referring to a variable that's already been defined. We know what you're talking about. Whereas over here, it's like, sum? What do you mean? What's sum? Because it's not within the scope of digit degree. It's only within the scope of digit sum. So basically, only the variables every variable that's defined in digit sum is not going to be accessible outside of digit sum. Okay, so normally functions are like that. That's kind of a default behavior for functions. But other blocks like a for loop or an if statement or something like that don't normally really have that scoping behavior. But that's what let and const do. So when I'm using a let instead of, for example, using a var, on the var, it's going to be no problem. I'll say, yeah, okay, I know the degree you're talking about. So, maybe you could argue this is a better way to do it. But let is, it's kind of a nice thing. I mean, I like the idea of the block scoping. I think it's a little safer overall. So I kind of prefer doing it this way. I realize it might look a little awkward having this kind of empty space at the beginning of the for loop. So sorry about that, but I think it's worth it. Okay, cool. So that passed. We had a nice big success. Everyone is very happy. Let's archive this one for now. Actually, here's what I'm going to do. I'm going to copy it. I'm just going to pop this new copy up here. And now, basically what we want to do with this is make a few improvements. So the first thing I want to do is this stuff up here. The way we're getting sum, I'm thinking about it and I'm thinking, isn't there an easier way? Is there a way we could do this that's like, that doesn't involve a loop or something like that? It's a little more direct. And yeah, so let's try. And evidently I'm confident in this because I've already written down the return. So I'm thinking we can probably do this in one line. Let's do num dot, okay, there are a few ways we could do this. So we could say num dot toString. So that's going to turn it into a string. And then we could do a split to turn that into an array. And then from there, we could do a reduce to add everything up. A and B is going to get mapped to A plus B. Okay, so we could try something like that. Let's just check to see if digitSum is still working. So what do we have? 125, which should give us something like 8. And we're not getting 8. We're actually getting 125, which is weird because it's not any different than this. And we're also, like, to make it especially weird, it's a string. So those might seem like kind of, two problems, but it's actually kind of, the two are related, and one almost gives us an idea of the solution to the other one, because if this is a string, if it's interpreting the 1, the 2, and the 5 as strings, then it's not looking at this as being an addition. It's not looking at this as adding two numbers up and finding the sum. It's looking at that as being a concatenation. So in other words, putting two words together. And when I say words, I mean strings, and strings might have digits in them, it might be numbers like it is in this case. So basically the idea is that this is concatenating. It's saying, oh, here's a string, here's another string. You want to concatenate those? It's just like, if I were to do like, hey, plus, what's up? Something like that. That plus is not going to add these two things together. It's concatenating them. It's putting them together as one string. Okay, so that's really what was going on up here with this plus. So let's get this back where it was, 125. And just to sort of be clear about it, I'm going to say this is a parseInt. It's the integer version, not the string version. And same thing with the other one. Why did it think they were strings? Well, it's because we converted them to a string right here. And why did we convert it to a string? Well, so that we could put it in an array. That's basically the idea. So, I could have done like a dot map, and maybe that's the better way to do it. Like just dot map and convert it to a parseInt, and then do the reduce after that. But I'll do it this way. We'll see if it works. So good. That's giving us 8. That's a little closer to what we want. Okay, so cool. That's what digitSum is all about. We could make this even like a little shorter. We could say like constant digitSum is going to be something that takes num to an output of num.toString and the rest of all that. And we'll see if that still works. And it does. Okay, cool. So is there a better way we could handle this? Well, something I personally have a bit of an allergy to is this, the dot split. I just feel like it doesn't really get the point across that we're turning this into an array when we just do a dot split on it. So instead, we could do something like this. I'm going to put our num.toString in parentheses, and we can do like an array.from. And that makes it a little more clear that it's going to be an array. I can see like it's implied by the wording here, so I think that would make a little more sense to the reader. But we can get it even more like compact. We can use this spread operator we've been getting a lot of usage out of. Spread operator doesn't just work on arrays, it works on strings, and I think other iterables. And so the idea is now we're taking this string, and by using a spread operator, we're breaking it into every one of its characters and using those as arguments for the next thing that it's being passed into. But it happens to be passed into an array here. So using an array literal, this again sort of implies, yeah, this should probably be an array. Okay, so we'll run the tests on that one. And cool. Nice. It's still looking pretty wide though, so maybe there's a different way we can do this. And okay, I'm probably going to undo this afterwards, but I do want to show you kind of a sneaky thing we can do here. So we've got our A and B. Let me just get a little more room. There we go. Check this out. A times 1 plus B times 1. And that probably seems really weird. Like, why multiply it by 1? Isn't that going to make no difference whatsoever? But it does make a difference. And the reason is because A and B were both strings in this case, right? A was a string, B was a string, just containing, digits for this example. And so basically when we multiply it by 1, that is unambiguously mathematical, right? So just like we were saying, the plus, well, maybe it means addition, maybe it means concatenation. It depends. It's context dependent. Whereas this multiplication, no, that's not context dependent. That only has one context, and it means multiplying by something. So if we see like a string, in fact, here, let me demonstrate this. If we had a string that was like 5 and we multiplied it by 4, let's say, What are we going to expect from this? Like a 5, 5, 5, 5? No. It's 20. It just typecasted. It's saying, well, okay, multiplication would make absolutely no sense here. So if this is a string anyway, so they must be talking about this as being a number. So let's just multiply that by this other number here. And that might seem strange if you come from like the background of a different language where this actually would like multiply the string, so to speak. Like if it would just put 4 5s in a row. And JavaScript does have a behavior like that, but it's using repeat. So, you know, if I were to do something like this, then yeah, I would repeat it 4 times. So other languages will do that sort of thing when you do multiply by 4, but no, not JavaScript. It only uses multiplication for numbers, so that's why when we see something like this, it knows, oh, must be talking about numbers. Okay, so let me do some undos here, get it back to the way I had it. There we go. Okay, cool. So, all right, I'm actually going to use neither of those, and the reason is because I want to do this sort of one step at a time. So we'll put a dot map in here before the dot reduce, and the dot map is just going to say x gets mapped to parseInt of x. I think that actually is a little bit shorter than the way we were doing it before, like having the reduce do a parseInt on a and b. I could be wrong though. It's probably about the same. Anyway, we'll just space those out a little bit. Maybe like if we could put these over here. Yeah, that's much nicer. Okay, cool. That looks kind of neat actually. Don't need all that space anymore. Okay, so let's run that. Let's see if the digit sum is working. It's working. Okay, great. So let's get rid of that and we'll see if this all still works. I mean, this is the stuff we were doing with digit sum. Oh, yeah, it's working. Okay, so let's submit that. And we'll see if it accepts it. It accepts it. Okay, great. So that feels good, I think. Yeah. All right, so let's see. At this point, I mean, we've really, I think in some ways anyway, we've improved the digit sum algorithm. Actually, okay, I shouldn't really even use the word improved here because I actually don't believe that this version here is better than this version down here. I actually really like this version. I like the way it keeps it numerical the whole time. I feel like it's minimizing the amount of calculations that we have to do by just going through with a loop, just going through the number one digit at a time and just adding them all together. I kind of like the simplicity of that, the kind of mathiness of it, I guess. Whereas this one, this feels like some functional programming kind of stuff, which is cool, but, you know, it's... I just feel like, you know, we're taking this number, we're turning it into a string. We're turning a string into an array. We're turning the array of strings into an array of numbers, and then we're adding up all those numbers. It's kind of like a lot of conversions that feel sort of like, I guess, superfluous. We don't really need to do all those, right? We could just keep it numbers and just count up the sum that way. So I actually do prefer this, but that's personal preference. You know, maybe you like this better and that's fine. All right, so either one of these is okay. It's up to you. But the thing is, I don't just want to improve this digit sum function. That's not the only thing I want to do. I also want to think about a way that we could sort of just improve the algorithm overall. So one technique that's been, I guess, a little bit en vogue here at JavaScript the Game is this strategy of using dynamic programming. So we've talked about a few dynamic examples. We did them in task 33, and then again more recently, I forget the number, but it was knapsack light. So I don't know if that was 40 or 39. It was a recent one though. Anyway, the point is, for both of those we did dynamic programming. Now, we can use a dynamic programming implementation for this problem as well. It's going to be totally possible, and it is something we're going to do in just a sec. But before we do, I have to say what we're going to do for this one. We're going to be working on a one-dimensional dynamic programming implementation. So I'm just going to get that started. I would really recommend, if you haven't watched it yet, watch the task 33 video, because there's I think a pretty solid intro to dynamic programming in there. And in particular, we look at, I guess, a total of 3 examples. We look at a one-dimensional one, a two-dimensional one, and then a two-dimensional one over a bit mask, which is like pretty heavy stuff. But anyway, the point is, for now, we're going to be looking at this one-dimensional example. Basically, if you haven't seen this before, the idea is that we're going to use this to break down the problem into a set of overlapping subproblems. Now, specifically, the way I want to do this is instead of just finding the digit degree for the number n, like the example that they supply, like the 91 or the 100 or the 5, instead of just finding the digit the digit degree for the number they supply, I want to find the digit degree for every number up to and including that one. And you might be thinking, oh, well, that's like overkill. It seems like a lot. Will that even pass the test? I mean, haven't you noticed this goes all the way up to 1 billion? Well, yeah, I mean, I'm up for the challenge. We'll see if it works or not, but I guess we got to give it a try is the main thing, right? Okay, so basically, here's the idea. We're going to have this dynamic programming array, and we're basically just going to insert 0 for any number that isn't greater than 9, right? That doesn't have more than one digit, because it's already there, just like the 5 that we saw over here, right? I mean, it had a digit degree of 0. It didn't take any digit sums, any iterations of the function digit sum, to get it to a point where it's just a single digit. So basically, for dynamic programming, we're going to have a bunch of zeros, like 0, 0, 0, 0, 0, 0. So let's get started on that. So we'll start loading this up, and we'll say for let num be assigned the value of 0. Num is less than or equal to n. It's going all the way up to and including n. And here, we'll do something like this. So basically, okay, we'll say let next be assigned the value 0. And this is going to be the number that we're going to be putting into this dynamic programming array. And I guess just at the end, we're going to return dynamic programming just to see what's in there. But eventually, we're going to do something a little bit different. And I'll say, well, if n is greater than 9, then we're going to do something. But otherwise, we're just going to push this right into the dynamic programming array, so we should get a bunch of zeros. Okay, so that is actually the way we want it to look. This one, not so much. We want some non-zero stuff in here. So, okay, what do we want in there? Well, okay. Basically, the idea is this. If n is greater than 9, then we can sum the digits and we'll get something, right? So, like, for example, let's say n was, I don't know, 14. Okay, let's say n was 14. So if n is 14, then we'll add the digits. So maybe I'll say let sum be assigned the value of digit sum for, wait a minute, not if n is greater than 9. Num, there we go. That was a close one. Okay, so sum is going to be this thing over here. And then basically the idea is sum will necessarily be something we've already calculated, because sum is going to be less than num. You're not going to find a number whose digit sum is greater than the number itself. Okay, so what I mean by that is you'll never find a number where if you add up all the digits, you'll get an even bigger number. That's just not something that happens in math. Because of that, that means once we've reached this, because we're going all the way from 0 up to n, right? So like by the time we reach n or whatever number we're talking about, we already know the digit degree of everything up to that number. So because of that, after we find sum, we can just say, well, the digit degree here, like next, this thing that's going to be the digit degree for this number, it's just going to be 1 plus whatever the digit degree was for the sum of this thing. So like, for example, let's say we're looking at the 91, right? And we say, all right, well, that is greater than 9. Okay, I guess let me put it this way. if we're talking about the 91, we're running this algorithm on it, then basically when we get to the point where num would actually be equal to 91, and we will do another iteration for that because it's less than or equal to, but when we get to that point where num is the actual 91, well, that would mean that we've already filled this dynamic programming array with the digit degrees for all the numbers up to, but not including 91. So from 0 to 90, we already know all of them. Okay, so then basically the idea is, since we already know the digit degree for all the numbers up to including 90, so we get to 91 and we say, all right, well, 9 plus 1 is 10. So, well, we already know the digit degree at 10, right? And it would be 1. So then just add 1 to that. 1, because we did a digit sum here, plus the digit degree of whatever that sum was, because it's just one extra step to get to there. We've already calculated how many it takes to get to a single digit from that sum. Okay, so that might seem a little complicated. Let's run this anyway. Let's see what's going to happen. Okay, not looking any different. If we look at this one over here, it is looking different. So from 0 all the way up to including 9, we get a bunch of zeros because they're already one-digit numbers. After that, so for 10, 11, 12, 13, 14, 15, like basically for everything less than 19, so from 10 to 18, we're going to have 1, because if we add up those two digits, we're going to get something that's one digit long. But 19 has a digit degree of 2, because 1 plus 9 is going to be 10. That's still a two-digit number, so then we have to go 1 down. But again, the way the dynamic programming works is it says, okay, so we've got 19 here. What's the sum of 1 and 9? Oh, it's 10? Okay, and what was the digit degree of 10? Oh, it's 1. Okay, so we'll do 1 plus this 1 here. That gives us the 2 over there. Okay, so great. That's nice. I'm going to keep this. So the dynamic programming array, I'm going to console log it. But really what we're looking for is the last entry, right? At n, what should it be? And notice the 1 we're getting here is the same as the 1 we're getting here. That's probably not a coincidence. So let's run the tests on that and we'll see where it takes us. Okay, very cool. So, nice. It's passing all the visible tests. Let's see if it gets the hidden test as well. And I'm not sure if it will. I have to say I'm a little curious. Okay. Syntax error. That's actually kind of surprising. I was expecting more something like a timeout, but let's see. Maybe there was something that we did wrong or something like that. Let's try just reassigning n, I guess. So we'll say n is going to be 100,000. I suppose I could have just typed in 1E5. That would have worked as well. Okay, so, well, good point. That does have a digit degree of 1, because once we add all these up, we just get 1, which is a single digit number. So, okay, maybe that's not the best example. Let's try a different one. I could try like a billion, but again, it's just going to have a digit sum of 1. So instead, I'll try 999,999,999. So a billion minus 1, basically. And we'll run that. And I'm curious about if it's even going to get there. Something tells me it might time out. No, it actually is saying syntax error. So, that's kind of strange. I wonder what the syntax error is. Well, okay, first of all, I have to imagine it's not truly a syntax error, because if this was a shorter number, it works just fine. So I'm assuming it's some kind of overflow thing. You know what? I'm curious if this is actually causing the problem, because sometimes we do get that kind of thing happening where there's like too much, there's like an overflow of output, like we're trying to output too much at a time. So that could be the issue. No, I guess it's not. It has something to do with the number being too big. I wonder how big is too big. So this is 7 9s in a row here. Yeah, okay, so that was fine. Let's get another 9 in there. We'll push our luck. So this is 99 million. Okay, that's where we're getting the syntax error. So it's something that's happening for really big numbers. I don't know. I have to imagine it's probably something to do with more of a timeout, or maybe it's like running out of memory. Like, I don't know if JavaScript can support an array of 1 billion elements. We'd have to Google that. But anyway, the point is, this wasn't a good example of a problem, this wasn't a good example of a dynamic programming candidate to begin with. I mean, it's kind of cool and all using dynamic programming. It's cool to sort of get the hang of it and get a better idea of how it works when it's applicable. And the reason I say it's not applicable here is we're actually creating way more work for ourselves than we need to. Because if you think about it, if we have a reasonably large number, like even 91, look at the size of this array, like this is pretty big. I realize the point of this is we're trying to save ourselves from having to repeat digit sum a whole bunch of times, right? Because we're sort of thinking like, okay, so for something like one of these, we're doing digit sum until we get down to a one-digit number. So that could take some time, right? But think about it. The biggest number we're going to encounter, what was it? It was this one. So that's 9 nines. So that means this would have a digit sum of 81. 81 has a digit sum of 9. So this thing's digit degree is just 2. That's it. So we don't need to worry about doing this a whole bunch of times. The maximum number of repetitions of the digit sum function that we're going to encounter would be for this number right here, because it's the biggest one that we can find, or it's the one with the biggest digit sum that we can find. And even this one, it doesn't really take very long to get to a one-digit number. Not long at all, just 2 repetitions. So, okay. I guess we don't need to worry too much. We're probably not going to have to call this more than 2 or 3 times. Okay, so because of that, this is major overkill, because we're saying we don't want to have to repeat this digit sum function too many times. But the thing is, if we're doing this, if we're using the dynamic programming strategy here, then we're doing this up to 1 billion times. We're doing this for every single number. I realize we don't have to do it multiple times for the same number, but we do have to do this for every single number. And so it's just not going to be an efficient way to do this. So this is not a great candidate for dynamic programming, but I'm glad we did it because it gets the point across, and it did work for very small numbers. So yeah, okay, I do have to keep this one blanked out. I'll say dynamic programming algorithm works, overkill. Works for only small values of n. Maybe overkill is not appropriate, because overkill would imply that it doesn't just get the job done, it gets way more than the job done. It's probably more than you needed for the task. We're not really trying to say that here, because it's more that we're trying to say it's underkill. It didn't work, right? So I'll say not really applicable. Not really appropriate. Yeah, not really appropriate for this problem. Works for only small values then. Okay, cool. And then we'll just, I guess we'll just take this one and resurrect it, bring it back up to the top, and I'm doing that so that I can actually submit the code and have the comments saved and stuff like that. So we learned a valuable lesson here about dynamic programming. It's cool, it's magical, it often helps us out a lot, but this is not one of the situations where it's going to be super applicable. Even though it does work for small values of n, it's not saving us any effort. It's actually increasing both the time and space complexity, so not the best. Okay, so we're going to wrap up that one for now, and in a minute we're going to